In this paper, we present a novel method, coarse and fine-grained attention network, for generating high-quality crowd density maps. Given a crowd image, crowd counting is to estimate the density map and the total people count. The value of each pixel in the density map reflects the density of the corresponding area in the image, and the people count can be obtained by accumulating the values of all pixels. For ground truth density maps, each labeled height is substituted with a Gaussian kernel. The kernel is normalized to 1, so the integral of the density map can be considered as people count. Existing methods have two disadvantages. Firstly, the influence of the background is not fully considered. Convolutional kernels may extract features in the background that are not related to the crowd, resulting in misrecognition. In this case, accurate people count may be caused by the underestimation of the crowd region and the misrecognition in the background region. Secondly, all crowd regions are treated equally. In fact, when a person observes a crowd image, it's normal to pay different attention to different areas. That's because for areas with a high degree of occlusion, it's more difficult to distinguish the features of each person, thus worth more attention. To solve the above two problems, we designed a mechanism that can suppress the influence of the background and assign attention weights to regions with different density levels. The overview of our method is illustrated in the figure. It consists of 4 modules. Feature map extractor is used to extract general feature maps. Crowd region recognizer is used to classify people and the background and produces coarse-grained attention maps. This module tries to solve a two-class classification problem. The goal of the density level estimator is to further classify the crowd area into different density levels and produces fine-grained attention maps. We divide pixels in the crowd area into 5 categories and consider it as a 6-class classification problem. Ground truth for 2 classification problems is obtained according to the threshold from statistics. The density map estimator is for regressing density maps. Feature maps in this module are refined by coarse and fine-grained attention maps mentioned above, with multiplication at multi-stages. We introduce a multi-scale structural loss that considered both structural similarity and counting accuracy. SSIM or high-resolution density maps can focus on spatial details and improve structural similarity. SSIM or downsampled density maps can improve local and global counting accuracy. To reduce false recognition ratio, we also add a background-aware loss item, the ratio of background and total people counts. The final loss function is a weighted sum of the density map and attention map loss functions at multiple stages and background loss item. The weights of these components are dynamically adjusted in the training process. Our method reports superior performance on 4 major datasets under MAE and RMSE criteria and is also effective in suppressing the false recognition in the background area. Some feature maps from internal layers are visualized. Refined feature maps in the last column retain most features in the crowd area and discard unrelated features in background area and help reduce the false recognition ratio. That's all. Thanks for listening.